It's been quite a process over the last few years, but I thought I'd do a little bit of introduction information first. Many of you knew this product line and our participation over the last 40 years as BSD Medical Corporation. But about 4 years ago, the two divisions of BSD Medical Corporation were divided into two different companies, and the Hyperthermia group and division and product became part of the Pyrexar Medical Group. This is going back a few years when the original 1978 development group was organized at the BSD Medical. I know you want to recognize me in that little circle, but there was a very dedicated group in the early days. Back in those days, we really didn't have computers like we have today. And so it was quite different in starting up a new company. Since the last 4 years, Pyrexar Medical has expanded the distribution throughout the world by a factor of more than 2 times. So it's been a very active group in getting hyperthermia support going around the world. Just to mention a few things, Mark Falkowski, the CEO of Pyrexar team, has led us in doing several things in just the last 4 years, substantial upgrades and retrofit of the BSD 500 systems with a new applicator arm, new large screen, touchscreen monitor, new software with user interfaces that are much more modern. The redesign of the BSD 2000 3D MR system, you've seen pictures of that. We call it the universal system, where we've removed the patient support sling so the patients can be adapted more easily to various MR patient support structures that are common with the MR systems. So they would rest on pads rather than the sling. This helped to reduce cost for implementing new systems with MRIs and providing this universal compatibility. Another project we'll speak about more tomorrow is the HALO phased array for the brain tumors and other potential brain diseases we're going to be researching. So that'll be a tomorrow presentation. But what this talk is about is to kind of reflect back with a little bit of entertaining thoughts of what the history has been and how some of these deep heating has been developed over the years. 40 years ago, the deep heating hyperthermia systems that were kicking around and being used, one of them was the magnetrode. This was a single churn inductive loop that operated around the 13 megahertz region, and they felt that they were heating deep central tumors. But of course, they were not measuring the temperatures at depth, like sometimes even today we find in systems. But as we did research on this system and looked at the physics, we realized in phantom testing and modeling that there was no central heating. And eventually that was taken off the market because it was only a superficial heating technique, creating eddy currents. Also, back in those days, capacitive RF electrodes were being used. And in fact, the RF electrode technique of treating tumors, cancerous tumors in the body, began early by Geyser in about 1917, where they would apply RF electrodes to the surface of the body and heat therapeutic heating for tumor treatments. More recently, that's also happening in today's world. Back in 1974, Bill Guy published in the IEEE a study with these capacitive electrodes where he pointed out the substantial heating in fat layer, where he concluded that it would produce more than 17 times greater rate of temperature rise in the fat heating than in the muscle underlying. With some of these work and efforts that were published at the time, we realized that we needed to look at something better than that for future systems. So that was back in the days, early in 1917, of the horse and buggy. Well, nowadays, we see much of the same technique being used. The little picture on the left I kind of like because it represents a horse and buggy in a modern form where it's been repackaged into a more modern look. And that's kind of what the modern capacitive heating systems are today. They're the same basic system, doing capacitive heating with maybe a little different modern look to them. This is a typical system of today. One thing about the two electrode systems, there's been numerical studies performed by various individuals, and one study that was by D'Ambrosio used blood flow models of the fat and underlying tissues, but concluded that the calculations he had done showed that extremely high temperatures, up to 60 degrees centigrade, are reached in normal tissues, including the fat layer, of course, if therapeutic temperatures were to be obtained in deep-seated tumors. This is because of the high impedance of the fat layer. Other recent work that's been published as well by Petra Koch that has concluded that although this is about the electrode systems, although this study showed that capacitive heating is in general much less effective compared with radiative heating for deep-seated tumors, capacitive heating can be of clinical value for some specific patient categories. I think sometimes those specific categories are not identified when they're being used clinically, however. And went on to say this simulation study showed that therapeutic temperatures are predicted for capacitive heating in patients with almost no fat. Nevertheless, radiative hyperthermia generally yields much more favorable heating patterns for deep-seated pelvic tumors compared with capacitive heating. Important conclusions. Well, jumping back to the past, back in the days of 1979, many of you don't know about this, but computers were not readily available. You just didn't have computers accessible. And so it was quite an accomplishment for us to develop the first computer-controlled hyperthermia system using the good old Z80 processor. That's what it looked like. Back in those days, though, we were looking into how we can do deep hyperthermia using a radiative method. And so back in 1980, we developed a prototype, a small-scale version of a TEM cell where we did some inertial evaluations with, realizing that we could achieve deep central focusing. That was actually included in the patent in those days. But we realized that was probably not the thing that would be wanted to be used in a clinic. Although in Utrecht, Lagendijk in 1983 actually built one of these models for them to use in early clinical work. Now, one of the first deep phased array concepts was developed back in 1979 by a young guy there. That's a 6 pyramidal waveguide structure. But it was not with the intention of just treating arms. It was to develop something to show the principle so that we could take that to larger arrays for the deep areas of the body. And that eventually led to the full-size annular phased array development in 1980. This applicator actually had 16 TEM mode pyramidal waveguides formed in 2 rings of apertures. These were loaded with high dielectric field apertures operated from 60 to 120 megahertz. And some of the old timers like me will remember those early days. We actually had 3 separate water bolus bags around the patient. These are some of the early development assembly pictures of these structures as we were building them. And on the right here shows just a diagram of the 2 rings of the pyramidal waveguides. So use of waveguides have been around for a while, since 1980. This is showing some of the construction taking place, but back in those days we didn't have good numerical models to study what was taking place. We did some work on our own to develop some numerical models to evaluate the potential, but we had to make phantoms, both cylindrical phantoms. We had fiberglass full-bodied mannequin phantoms filled with saline or with tissue equivalent muscle phantom, in which we would then measure temperature. An early example of this is shown here, where we would have a fairly large sized body male, in this case, being heated with 74 megahertz with the metal waveguides. But we found that using the waveguide approach actually tended to increase the stray fringent fields, leading to additional SAR heating in the neck. However, the neck actually had quite high blood flow, so that was generally not much of a problem, and we always used a water bolus around the neck as well to mitigate that. But eventually we eliminated that by the new designs we had with the dipole arrays. In those days we had other forms. There were female mannequin forms that we were testing to show the focusing, saline field, so we could scan it completely with E-field sensors. We would use cylindrical phantoms and place inside of these saline phantoms various objects of like nylon rods and things to study how the deep tissues of the body might perturbate the electromagnetic fields. And of course we found time to do some animal testing. And this is just a case where we had done heating in the thoracic region of a pig to demonstrate selective heating in the central region of a lung site. Again, this was published back in those days. On the left, we had numerical modeling we were developing to predict in muscle phantoms, distribution at different frequencies, as well as the lung example in a pig and also in the pelvic area. These pigs, however, in these tests were sacrificed before, so they had no blood flow. We were looking at SAR distributions. This is the early configuration where we actually had patients lying on a support couch, but later developed the sling technique that we have been using in more recent years. The dipole phased array concept was early on developed by us in the form of a mini annular phased array where we had 8 dipoles surrounding a limb area of the body that operated at between 100 and 180 megahertz. As shown here, we developed this and could do selective central heating. This was an early crude version of the water system that was connected with this applicator for limb treatments. An example of other phased array systems that have been developed during this period of time, early on in the 1980s, the 4 waveguide systems of the AMC4 system were developed, operating at 70 megahertz. You're familiar with that, and that's been talked about. And then later, the AMC8 has been developed. Again, another waveguide approach similar to the APIS original design that we were working with. As we were looking at the questions of what should we do next in the progression of this, we realized that the annular phased array was a very bulky, almost frightening structure for a patient to look at. I'm not sure if the AMC4 has the same thing, but we thought there's got to be a better way. And so consulting all the experts that we could, including a familiar face that you might recognize, young Gerard Van Roon, we eventually came up with a design using the 8 dipole array and the Sigma 60 for deep focused heating in the first BSD 2000 configuration introduced in 1988. Since that time, every part of this system has been substantially upgraded, modified, and made more modern, but that's the systems that stood in 1988. We have been conducting deep studies with numerical models in more recent days using COMSOL 3D multiphysics to evaluate the characteristics of these phased array systems and other deep heating systems, primarily using homogeneous phantom cylinders or elliptical shaped cylinders, either muscle filled or saline filled. Normally we do these simulations using the dielectric of either muscle or saline and 2/3 muscle conductivity at the particular frequency that we're working with. An example of this, you've seen this before, where this was an example of the 100 megahertz standard operation for the Sigma 60 applicator, showing the numerical model results with a very large heating pattern size with central selective focus. You'll notice there was some edge fat heating, but only 50% of the maximum SAR in the center in the fat of this 100 megahertz configuration. When we lowered the frequency, as that was a broadband applicator, to 75 megahertz, fairly close to the AMC4 frequency, we found that the fat heating near the surface edges of the bolus interface began to grow substantially larger compared to the center focus, but still was very suitable for deep heating as shown here. We applied this same model because we were kind of curious, well, what would the 4 waveguide approach at 70 megahertz be with the 40 centimeter long water bolus that is used at the AMC4. It was interesting to see that in that particular model, using the same phantom structures and everything, it was predicting 100% of the fat SAR being present compared to about 50% in the center focus with equal phase focusing. So we felt that we were probably normally operating in the frequency range closer to 90 to 100 megahertz with our Sigma 60. We were curious also about, well, how about the capacitive electrode system capabilities now that we have numerical modelings and could do multi-physics studies, but in our studies we found that we really had no deep central focus possible using this 1917 technique of 2 electrodes. Again, our models were showing that 100% value of the SAR was occurring in the fat. Directly underneath the fat and the muscle layer in these phantom studies, it had dropped to about 8% of the 100%. because of the high resistance of the currents that flow through the fat layer. In this particular model, the electrode size was smaller than the diameter of the phantom. Thus, there was a fair amount of fringent fields demonstrated that resulted in as low as 1% of the SAR dropping to the central area of this homogeneous phantom. And this just shows the details of the size of the phantom and everything. This was actually a log plot, so we could see what the value was in the center. We applied also, because we were curious, well, what's going on with the temperatures, and we used a blood flow model with thermodynamic effects going on, and with the 1 centimeter fat layer on the left, we were finding that we were still getting quite high fat, even though we were trying to apply a 10 centigrade water interface on that bolus interface. So, and we thought, well, let's try 2 centimeters of fat, and it got even worse. We were getting temperatures at 67 degrees, and is what it was taking for us to get anywhere close to a therapeutic temperature deep. But I want to talk a little bit about something that hasn't been talked about a great deal, and even some of our own users have misunderstood somehow how the dipoles really work in a sigma 60 or this type of an array. Commonly, you would think of a dipole radiation pattern being a circularly symmetric pattern around the dipole, where it would radiate in all directions as the wave propagates away. Well, that wouldn't be very good for a hyperthermia device, because you're going to be throwing all this power out into the air. But that's not really what's been done, because we have a way in which we can cause the dipoles to be highly directive into the central region where the water bolus is. I'm going to explain that in detail so you can understand, so forgive me for the detailed explanation, but I thought it's good for people to understand this. First of all, antennas that are very short in length are not very effective radiators. And so keep that in mind. If we have an antenna that's a very short radiator for air, you're not going to radiate out into the air space compared to radiating into the high dielectric space of the water. Making it like a half wavelength or full wavelength dipole, you have good radiation when you're loaded down with a relatively long wavelength antenna between a half wavelength to a full wavelength. Secondarily, the antenna water versus air intrinsic impedance has a loading effect of these dipoles. So on the outside, you have the intrinsic impedance of 377 ohm. I'll just go through this again. So on the first case, the BSD 2000 radiation field is selectively directed into the water bolus region and not into the outer air, because the dipole lengths are too short for efficient radiation into the low dielectric plastic and air that surrounds it. The water has a dielectric of 78, thus at 100 megahertz, the wavelength in water is about 33 centimeters, shortened by a factor of 9 compared to 300 centimeters in air. An efficient dipole radiator should be less than a half wavelength of the media. So the sigma 60 has a 44 centimeter dipole, 45 centimeters of water bolus. The sigma I, it has actually a 14 centimeter dipole with a 45 centimeter bolus. So that it tends to not be a very efficient radiator in either one of these into the outside air. Number two, the free space radiation impedance is 377 ohms per square, and water is about 43 ohms per square. This means that the side of the dipoles with the water represents a low impedance, like a parallel electric circuit. The loading of the high dielectric air impedance, however, is really too high of impedance to couple much of the power. So when we think of this, it's like a simple electrical circuit. So that the radiated electric power, the field that's created by the dipole, one side being loaded by the plastic and air with low dielectrics, is like a parallel 377 ohm resistor in electrical circuit. The other side loaded by the water, it's like a 43 ohm load, meaning that most of the power automatically would be delivered to that low impedance direction. So these two mechanisms help to get directivity provided for these thin, transparent plastic shell applicators. And this is a more current view of the modern BSD 2000 configuration, showing the Sigma 30, the MAPPA, same design as the MAPPA originally, the Sigma I, which is the 24 antenna array with 3 rings of dipoles, as well as the Sigma 60. Each of these has again been redesigned substantially over the years. We show here the Sigma Ellipse that is similar in the dipole forms with the Sigma 60, but has a lower vertical size for less pressure on the patient. Originally, we had a large tube amplifier, 2 racks of this, but it's all reduced to a solid state amplifier now, the Dodic or Tetra amplifier. We redesigned the Sigma 60 in recent years to improve the handling with a larger bolus membrane, end-ring bolus support and seals that make it much improved for field servicing, and a larger air purge zone in the top with continued this very rapid drain of the water when needed. This is just an example of the Sigma I that has the 24 dipoles arranged in 3 rings that provides us now not just 2-dimensional electronic steering of the focus, but a 3-dimensional control, shaping, and steering of the focus. An example of that is shown here, where on the left we have the more central focus where equal phases are operated, but if we shift the phases on the end rings, we can elongate that pattern to be a longer pattern through the central area. Or we can create a phase shift along the long axis as demonstrated by the figure on the right. The BSD 2000, and nowadays, because of this thin dipole design, it was envisioned to be compatible with MRIs, and in fact has been done so. Early on in Munich, we developed and put into place the first system that we did with a 0.2 Tesla system, showing feasibility of this system integrated with an MRI. And that was a qualitative, very good project as a first step. But then later in a collaborative project with Peter Wust and others in Berlin, we developed the BSD 2000 3D MR with a 1.5 Tesla system based on the Siemens Symphony system. And that was actually very successful in showing good, non-invasive, and accurate temperature monitoring with the MRI. The same system was put into place in Erlangen in 2007, and again in Dusseldorf in 2008. As an interesting step, we integrated in a research setting with Duke University with a GE Signet MR system on a cart-based type structure. This was never put into clinical operation. It was a research system, but showing how we could integrate this with a mobile cart on a GE system. Later, a similar system to Berlin had been put into place in 2011 in Tübingen. These systems are all still in operation at these sites, with the exception of Berlin and the research system at Duke. More recently, in 2014, we implemented this with Rotterdam with a GE 450W. That was implemented on a cart. You'll notice all these systems have this unique sling support for the patients. With that configuration, we realized that every time we had to interface with a different MR model or configuration, there was a significant redesign process that was needed to make sure we were adapting to the MR's patient handling system and configuration. And eventually we decided we're going to develop a system in these recent years that would be more universally adaptable to different MR models. And so we call this the universal system that is in place in Munich since 2017 with the Philips Ingenia 1.5 Tesla. Just a reminder about how we do this. A slide from Dr. Gellerman is helpful to show that we make this so that the hyperthermia system operates completely independent of the MR monitoring system. So they're very compatible. To do that, we had to design and install a special notch filter that's placed in the MR receive path to make sure the MR receiver would not be interfered with by the high power level that we operate at 100 megahertz. The receiver in the MR typically operates at 64 megahertz. Although those are fairly close in frequency, it required us to have special designs demonstrated by this. One of the critical parts is shown at the top is we needed to make sure that at the MR frequency we had minimal perturbation of the MR operation. So we developed this with less than 0.2 dB insertion loss at the MR operational frequency. And yet we had the notch filter dipping to about 90 dB to suppress the 100 megahertz transmission frequency of the hyperthermia system and its harmonics, as demonstrated on the right. So this system in Munich actually has an open access where the patient will, it'll be open, the patient lies down on these pads, closes and the water bolus fills, and makes it quite easy compared to a sling, a very stable situation. In fact, we think that using the support pads might actually reduce some of the patient motion artifacts that might occur from treatments with the sling, because patient motion might actually make a bouncing effect with the sling. Also in collaboration with Peter Wust and his co-workers, the Sigma Vision program was developed that actually do the subtraction image of the proton resonant frequency technique, demonstrated here with a limb phantom that was heated. And a great study that was done by Dr. Gellerman and her colleagues early on was to place a similar phantom with a rib or a bone structure with invasive temperature sensors inside of a gel-filled phantom where the MR would be able to monitor these fields, and at the same time we would measure the temperature with invasive temperature sensors with thermal mapping along these tracks. And an article was published showed how well the individual invasive temperature measurements were comparing and were agreeing with the MR measured temperatures, showing very good agreement. So that was a big step in helping us move forward. The recent system improvements I thought I'd mention briefly. Nowadays we have the MR thermal well that's being used for calibration instead of a temperature bath in our MR systems, making it much easier. This is possible by us pre-calibrating the sensors at the factory, so there's only a slight adjustment for calibration needed for them to be calibrated, but with a single temperature thermal well. We have semi-transparent shield rooms that we've developed that are used for non-MR systems, making it very easy to install, and as I mentioned, the universal MR configuration as well as simplified user interfaces. So in the past, these systems have used a water bath system for 3 temperature point calibrations, fairly laborious, highly accurate, but nowadays a simple thermal well provides this calibration and verification of our temperature sensors that of course is completely MR compatible. The water bath really wasn't MR compatible. It didn't like to have it in the room, so it was a little more difficult to use. This just shows the new construction technique of the standard shield room that we're using. It's a perforated aluminum metal structure, so it can be transparent. It can be installed very easily with no construction plans required. It's low cost, validated for 90 dB attenuation. You can use the existing heating and air conditioning of the room if need be, or something extra if you'd like. And it can be assembled quite easily in 2 days with 2 people. Going back to the old software look, this is the old software look that we've had with our original BS 2000 phase steering screen, and where we move the icon around in a patient model simulated by that ellipse. And this is the power amplitude steering screen that would be adjusted, and we could adjust all 12 channels in this way for the Sigma I. But the look was fairly cumbersome and cluttered, but the new software user interface that we've developed with the large touch screen with simplified graphics has been done where it looks a little bit nicer to work with, a much more modern look and less cluttered with information that's not needed to be viewed or worked with. So this is the view of our new phase steering screen. The power amplitude screen is shown here. Interest today is being generated by using HIFU for hyperthermia, not just ablation. I just thought I'd point out some of the differences between HIFU hyperthermia potential and the RF hyperthermia. The focal area of the RF phased arrays are a fairly large focal zone. Tomorrow I'll be giving a talk talking about how we are looking at changing some of that, making it smaller, but compared to the Rice size, focal size of a HIFU system, obviously. Much larger heating area is provided by the RF phased arrays. This provides much simpler focusing and steering mechanisms. It's very tolerant of air and bone interfaces, where HIFU is quite blocked by air and bone interfaces, creating also hotspots. So large tumors are quite suitable, but are quite limited for HIFU approaches. The dose monitoring compared to the HIFU we consider somewhat easy, where it's a little difficult in hyperthermia to control proper dosing with the HIFU approach. And the SAR patterns are quite uniform compared to the spot heating provided by HIFU. A new development that we've been talking about in the last year and working on is the HALO prototype project that we show here. It's a phased array with 72 dipole antennas surrounded head in 3 rings, and it's being used potentially for treatment of brain tumors as well as other brain diseases. This is something that is in presentations tomorrow afternoon, so I won't take the time now to describe this. It's encourage you to watch that. We've got some new results we can show that we haven't shown before when we do that presentation. But in conclusion, basically after 40 years, and I look back at these gray hairs I'm wearing, it's a long 40 years, but after 40 years, there's been a fair amount of development and progress that's just come forward in the use of deep phased array hyperthermia. Current progress have evolved to non-invasive thermometry and pre-treatment planning, numerical modeling, as well as the MR modeling and measurement that we've been doing. The maturity of the current systems has been changed and resulted in much reliable durability, uniform systems for treatments, providing a great deal of clinical utility with this system. And many times we have people complaining that the system just never seems to have a problem. It's very durable, very reliable, and that's taken these 40 years, I guess, to develop systems to where they are in that way, so that they're very utilizable for clinical applications. And I thank you for your attention, and hopefully this has been informative and helpful for you to understand.